All right, we are right at the start time, 2 o'clock Eastern Standard Time. So we'll go ahead and get started. First off, good afternoon. I'm Jason Thomas, project engineer here at America Makes, and your host for today's America Makes TRX webinar series. Just a little background on the TRX webinar series before I introduce our speakers. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium, called the America Makes Technical Review and Exchange webinar series, was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief question and answer session. If during the presentation you do have a question, please submit it in the Q&A space on the web, and I'll ask it during the Q&A session. I will do my best to get all of your questions answered. Today's webinar is on improved process parameter optimization using machine learning. This was actually one of our open project calls, and I'm excited to see this presentation. Without further ado, it is my pleasure to introduce Zach Simkin of Senvol and Taylor McKay of Northrop Grumman. Zach Simkin is the president of Senvol, the industry leader in data for additive manufacturing. At Senvol, Zach has overseen the development of Senvol ML, which is data-driven machine learning software for additive manufacturing. Zach's particular area of focus is on commercializing additive manufacturing data in ways that are valuable to industry. In addition to his role at Senvol, Zach has been called to serve in various leadership positions throughout the additive manufacturing industry. He serves as past chair for SME's Additive Manufacturing Advisory Board and on the governance board of America Makes. Additionally, he is a member of ASME's Technical Advisory Panel for Additive Manufacturing, the ASTM F42 Committee for Additive Manufacturing Technologies, and the SAE AMS AM Additive Manufacturing Committee. He has been published in top industry journals and has also been a featured speaker at numerous industry trade shows and conferences, such as Rapid, the Chem Show, and AM3D. Zach received a BA in economics from the University of Pennsylvania, where he graduated summa cum laude, and an MBA from the Wharton Business School. Taylor McKay is a principal additive manufacturing engineer with the Advanced Manufacturing Technologies at Northrop Grumman Corporation. Aeronautics sector. Prior to Northrop Grumman, Mr. McKay developed additive manufacturing materials, processes, and applications at Collins Aerospace, and has a thorough knowledge of various manufacturing processes within both the defense and commercial aerospace industry. Mr. McKay obtained a Bachelor of Science in Aerospace Engineering at the University of California, San Diego, and a Master of Science in Mechanical Engineering at Missouri to meet the ever-evolving needs of the world. Our 90,000 employees define possible every day using science, technology, and engineering to create and deliver advanced systems, products, and services. Zach and Taylor, I'll turn it over to you.
All right, thank you, Jason. Thanks, Taylor, for joining. This is Zach Simkin, everyone. It's pleased you're here. Thanks for joining us, and thank you to America Makes for hosting this webinar series. One really quick kind of housekeeping item. Taylor and I presented this content at the Rapid conference a few months ago. So we're doing it again here on a webinar series for folks who were not able to be there in person. We wanted them to still be able to see the content if they were interested. But I mention this because if you did see us present at Rapid, I wanted to let you know that this is going to be the same content. So I just don't want anyone to waste their time. So if you saw us then, maybe you want to tune out now. But for everyone else, look forward to spending the next half hour or so with you. So really quick contents. We're going to give a brief introduction, and then I'm going to go over a quick project overview, and then we're going to get into the technical results of a parameter optimization effort that we undertook. We're going to show you and talk about the machine learning approach. We're then going to juxtapose that against a more traditional approach for parameter optimization, and then we'll go over the technical results and a quick summary. But starting with the introduction. So this project stemmed from funding actually from America Makes, from an open project call. We at Senvol, we were the primes, but we had a fantastic team. So it definitely was not only us. We had Stratasys Direct Manufacturing, who did all the fabrication and testing on this program, and they were phenomenal. We had a whole host of people from Northrop, Taylor included, involved in this project in various capacities. We had NIAR involved. So the project overall was doing some things related to allowables, and NIAR has deep expertise and history is kind of one of the gatekeepers of allowables. So they were great to have on the project. And lastly was Pilgrim Consulting, which is a small business consulting firm led by Dr. Bill Fraser, who was a former chief scientist at NavAir. For those not familiar with Senvol, just a really quick background. We provide data-related products exclusively to the additive manufacturing industry. So, I mean, literally all that we do is data for additive. And our products fall into one of three categories. The first has to do with providing access to additive data. And these are different database products of ours. And we have lots of different databases with different tiers or caliber of data. But all of the databases are centered around either material properties or machine capabilities for additive. The next category is all about generating additive data. And we have a product there that helps organizations do so in a pedigreed or fully traceable fashion. And the third and final category is all about analyzing additive data. And there we have a machine learning software tool called Senvol ML that was used in the execution of this program, and we'll briefly talk about. So I'm not going to go into any great detail about our machine learning software tool, about how it works or anything like that, but it is the tool we used in this project. So I am going to mention it just on this one slide really quickly for situational awareness, because you'll hear us mention it a few times. But it's data-driven machine learning software specifically for additive. And there's a bunch of different capabilities in this software tool. It can be used to help rapidly optimize process parameters and develop materials, predict material properties, support qualification of machines and materials, analyze in situ monitoring data to help with quality assurance. And just generally speaking, it helps organizations minimize their data generation costs. And what's really important to know is that because the software is data-driven, it's agnostic in the sense that it can be used to analyze data from any additive machine, any additive material, or any additive process. So it doesn't matter whether you're doing a polymer on a material extrusion machine or a metal alloy on a powder bed fusion machine, our software tool can be used across the board. And in this particular program we're talking about today, as you'll see, it was used for polymer powder bed fusion. And Taylor, do you want to give the background on Northrop? You'll do a much better job than I will.
Yeah, thanks, Zach. Yep, Northrop Grumman, specifically the aeronautics sector, has been working out of, obviously, as shown here, for quite a long time, starting with, the well-known original oscillate type process and all the way up to current metal and different polymer processes. Done a lot of work to work with the DoD to develop specific materials and processes up to a point of maturity to fly parts in production, and continuing to do so with more innovative and newer and more innovative materials and processes today.
All right, thanks, Taylor. Now we're going to go over the project and then some of the results. So the presentation we are giving today, just to be clear, it summarizes the technical results of a parameter optimization effort that was undertaken as part of a larger America Makes program. So what we are talking about today in this presentation is not a summary of the overall program. Just want to make sure that's clear for those who have heard about this program and are interested in the briefing. Let me know. We can do that separately. But today we're going to be focusing solely on the parameter optimization task that was performed in this project. And the parameter optimization task was kind of a small piece of the overall program, but I just want to make sure it's clear that's what we're going to be focusing on today. So on this slide 11, I'm going to kind of illustrate what we did for this parameter optimization task. The first thing we did is we defined a parameter space. So we defined what it was we were going to investigate. And in this project, we investigated 6 different parameters. I know on this chart on this slide, you only see 3 parameters. That's just because visually you can't really see 6. But it was a 6-dimensional 6-parameter space. So we defined what we were going to explore. From there, we generated a whole bunch of training data for the machine learning approach. So each blue dot you see here is representative of a different coupon that was built using a different parameter set. So we had 300 coupons total, all of which were built with different parameter sets. and that was the machine learning training data. From there, the project team set a goal, which we called Goal A. And the specifics of what the goal are not so important, but just know we envisioned that we had some application in mind. The application had goals, and we called that Goal A. Once we had Goal A, we asked the machine learning software, hey, what is the best parameter set to use in order to achieve this Goal A? And the machine learning software tells us here, this red dot, this red point, that is the best parameter set to use in order to achieve Goal A. And we call that parameter set A, and it was optimized for performance. But we then did this a second time. We said, well, let's say we had a different application with a different set of performance requirements, which we call Goal B. Again, the specifics are not so important, but we had this Goal B, and we asked the machine learning software again, what is the best parameter set to use to achieve this Goal B? And it tells us we should use this parameter set here, this pink dot. And it's kind of a balance of throughput and performance because this goal was more about speed and less about performance. Now, in parallel to all of this, Northrop Grumman and their design team also did parameter optimization following a more traditional approach. So they had access to the same set of empirical data, all those blue dots, and they also tried to pick parameter sets that would best achieve Goal A and Goal B. And they selected parameter sets that were different than what the machine learning software selected. And at the end, we did a validation where we built a bunch of coupons using the machine learning software's recommendations. We built a bunch of coupons using the Northrop Grumman team's recommendations. And we saw, well, were the goals actually met by the parameters that had been selected? And that's what we'll be going over today. So we're going to start with the blue dots, the training data for the machine learning approach I mentioned. There's a capability in the software tool called the data collection protocol. And what that does is it intelligently recommends what data to generate. So it specifically tells you literally what coupons to build. And it's designing your experiments for you in a very optimal and efficient manner, far more optimally than more traditional design experiment approaches. And we have validated this numerous times, countless times. We, again, don't have time to go over that today. But there are two classes of algorithm within this DCP capability and within the software. The first is something we call naive DCP. And that algorithm tells the user what data to generate if the user is starting from scratch, meaning you have no pre-existing data. So if it's a new machine you've never worked with before, or it's a new material you've never processed before, naive DCP is used to design your very first build. And there's a different class of algorithm called subsequent DCP. And what that does is it tells the user what additional data to generate to optimally complement the data you already have. And so the subsequent DCP makes this recommendation based upon the analysis of the pre-existing data, as well as you telling the software what you want to accomplish. And the whole goal here is to maximize the improvement of the model's predictive reliability in as efficient a manner as possible. So with as little data as possible, we want to get as much improvement to the predictive model as we can. And so subsequent DCP is used to design your second build and your third build and so on and so forth. So that's what we use to design all the 300 coupons. And all the data that was generated, we had this build plan. We, of course, had a process control document that was used at each step. And in this program, we used 3D Systems S-Pro 60 machines, which again are polymer powder bed fusion. We used a nylon 11 flame retardant material called FR106, which is supplied by, I believe, ALM. We didn't do any finish, and there was a wet dry blast. For this program, we looked at Z orientation tensile coupons only, and they were ASTM D638 type 1 specimens. And lastly, here's a look at the 6 parameters that we varied and explored. So it was laser power, scan spacing, sinter scan, scan count, outline laser power, and then lastly, the XY location on the build plate. Here's a look at one of the build files. So on the left is the build file, and on the right is the completed tensile bars after they had been built. And this was from one of the machine learning training data builds. And as I mentioned, again, every coupon was built using a different parameter set. And so the build plan was as follows. We did 6 of these builds. So there were 6 builds of 50 coupons each for a total of 300 coupons. And those are the 300 blue dots I showed you earlier. We did use 2 different machines. So they were both S-Pro 60 machines, but 2 different serial numbers. So 2 different S-Pro 60s. Half of the builds, 3 of them were done on machine 1. The other half were done on machine 2. And as I mentioned, we used the machine learning software tool to design these builds and tell us which 300 parameter sets were most optimal to use. And the task at hand, as I mentioned earlier, was focused on analyzing the machine learning training data in order to optimize parameters to meet the different performance requirements. And so we set those 2 goals, as I mentioned, Goal A and Goal B for 2 different applications. The machine learning software was used to optimally select what parameters to use. And like I mentioned, Northrop Grumman's design team was tasked to also select optimal parameters for each goal without using the machine learning software. They were kind of used as a control group to demonstrate a traditional parameter development and selection approach compared to the machine learning approach that our team was using. And at the end, we did a validation build where we looked at how did the machine learning selected parameters and the traditional parameters perform. Did they actually meet goal A and goal B? Yes or no? And we'll find out. So on this chart 16, this is a look at the parameter ranges that had been defined for the project. So this was kind of the minimum and maximum values of what we were going to investigate in our parameter range. And based on this, there are over 219,000 different possible parameter combinations, which sounds like a lot, and it kind of is. But for additive design spaces, this is actually, in our experience, not considered that big. We've seen design spaces with millions, tens of millions, hundreds of millions of possible parameters to select from. In this case, it was 219,000, which is still big, but not as big as we've seen. And to select the optimal parameters to achieve both of the goals, both the Senvol machine learning software and Northrop Grumman, they had access to the machine learning training data. So both teams had access to those 300 empirical data points, the blue dots. And based on these 300 points, the question is, and what we're going to walk you through, how did the machine learning approach go about parameter optimization, and how did Northrop's team go about parameter optimization? So given that there were over 219,000 potential parameter combinations to choose from, how did the machine learning approach and the traditional approach go about deciding which were the best two parameters to achieve goal A and goal B? So now we're going to go over the technical results, and I'm going to start by walking you through the machine learning approach, and then I'm going to turn it over to Taylor, who will walk you through the traditional approach and the results. So the way it works on the machine learning side, it's quite simple. We take the data and we upload it into the software in a CSV file. We run the software and analyze the data to generate something we call an optimization tool, and you then use the optimization tool to make the parameter selections. All of this happens very, very quickly. Like, you can do this in minutes. So we spent less time on this task than Northrop Grumman did when they were optimizing parameters, but that really wasn't the focal point of the story. What we're going to focus on is the machine learning software's ability to optimally select parameters across an entire parameter range while also taking uncertainty of predictions into account. And so the software has a capability to analyze empirical data and create what we call an optimization tool. And I know it's a little small and a little hard to see, and there's a lot going on here, but I'll walk you through what you're looking at. In the optimization tool, row after row after row are different combinations of process parameters. So in this case, there were like 219,000 rows of different parameter combinations. And each parameter combination is mapped to the predicted output values and the standard deviations of those predictions for whatever your targets are. So you'll see here in column F, this is for the ultimate tensile strength predictions. So this column, this first number here under the column F, what this is telling us is if we use this parameter combination in this row, the predicted ultimate tensile strength value is 3127. And column G shows us the standard deviation of that prediction, which is very, very important because you don't want to only look at the average predicted value. You want to look at what that spread is, what the distribution curve looks at. And you'll see in a few minutes why that was so important in this case. So we have this giant predictive model. It's predicting our tensile strength, our modulus, our elongation, and our yield strength. And what the optimization tool is, what you're looking at, it's a surrogate model for the entire parameter range. So it allows you to investigate and interrogate literally every single parameter combination to find whatever is best for your requirements. And so a couple of key takeaways. Number one is the optimization tool enables Senvol or anyone using the tool to factor in uncertainty and consider the fact that each individual data point is part of a distribution. And the optimization tool also allowed us to evaluate and consider all 219,000 parameter combinations. And again, you'll see why that was so important when we compare that to the more traditional approach that Northrop undertook. And so ultimately, using a machine learning approach yields a very comprehensive and accurate method of optimizing process parameters. And as a reminder, where I'm going to leave you off, we had these two goals, goal A and goal B. Specifics, again, not so important. Just know we had these two goals. And where I'm going to leave you is the machine learning software, Senvol ML, selected the parameter sets it felt were best going to achieve goal A and goal B. So in this bottom chart here, you see parameter set A. That's the parameter set that the machine learning software recommended we use to achieve this goal A. And parameter set B is the parameter set that the software recommended we use in order to achieve this goal B. And with that said, I'm now going to turn it over to Taylor, who will walk you through the traditional approach and then the validation and results.
Thanks, Zach. Yeah, so we'll go over how Northrop approached kind of a more, at the time, traditional approach to down selecting parameters to meet these goals. So as you saw early on, there were these 6 builds of 50 coupons that gave us 300 data points, all at different parameter sets or varying parameter sets. And basically Northrop Grumman had that data all in an Excel sheet, different Excel sheets, used a lot of filtering methods to basically select and down select to a few options and then final options to determine which parameter set based on the empirical data alone to move forward with to meet goal A and goal B. And I'll just mention, as Zach said, it's not necessarily the time that was spent that was showing there. I mean, obviously, it probably did take a little bit more time than as the software would have to set that up. But but anyway, so going into goal A and goal B, our approach was, even though that the ultimate tensile had a range that was within the goal, Northrop approached to target a parameter set that targeted the highest ultimate tensile strength. And then for goal B, to minimize build time while meeting those property requirements, Northrop picked to minimize scan count and maximizing scan spacing. So a few things we wanted to kind of highlight as part of this approach is, since we were using purely empirical data, as Zach mentioned, of what Senvol ML takes into account, empirical data doesn't take into account uncertainty of a single data point, meaning that single data point, or even if there were 2 or 3, doesn't necessarily, no single data point is going to be the same every time. If you run same parameter set, multiple coupons, you're not going to get the same result. So that uncertainty of where that data point fell within a band of the actual results isn't taken into account. So that 1 or 2 or 3 data points that we're basing our selection on may run low or high and ultimately may not meet your goal. So it's obviously a less accurate approach. And we'll see what the potential consequences of that are. So to again highlight what Zach showed earlier with parameter set A and B that they selected, we're going to call our parameter set at Northrop A prime and B prime. And the numbers don't necessarily matter as much, but I'll just say, looking at them, you can see that what was ultimately down selected to are different between Senvol and Northrop. So let's see how those performed. So there was a follow-on build based on those initial results of 6 builds. And Zach mentioned this in the beginning of the presentation, but I'll just reiterate because you'll wonder, okay, what is all this other information here? This is part of a larger overall America Makes project. So there was follow-on activities after this. But the main point here is at the bottom, there were witness coupons. A certain number were selected, or a quantity were built and tested for each of the parameter sets. And I'll just quickly note that there were more built and tested with the Senvol ML parameter sets due to the additional follow-on activities for this project. Okay, so here's our parameter sets, and let's see how those performed. So for goal A, for parameter set A for Senvol, as you can see, you don't need to necessarily get into the numbers too much, but we highlighted whether it met the goal or not. And in this case, both ultimate and elongation, the goal was met for goal A. For Northrop A prime, our ultimate tensile and elongation were actually above the range that we were looking to target. And I'll speak to that in a bit. But for parameter set B, for goal B, for Senvol, again, the results show that both goals were met. Or all the properties were met. Whereas for B prime, for Northrop, again, not the case actually. Our ultimate was below what we were targeting. And the same could be said for the rest of the properties. So the other thing I wanted to highlight is how, so Northrop used empirical data, right, to select their parameter sets, whereas Senvol ML necessarily used that empirical data to then interpolate the whole design space and select parameter sets based on that. So what this is highlighting is the first column with empirical training data is saying for Senvol ML, parameter set A did not have any empirical data. There were no test specimens that were built and tested with that specific parameter set. But on the right, the Senvol ML predicted model mean, which is basically Senvol predicting what the result of that parameter set without any training data or without any data directly at that parameter set. You can compare seeing, the number there compared to the actual result is pretty close, as well as to the actual data, the average data that was tested for parameter set A. And this is a common theme for the rest of them here. So for Northrop, even though that we based it on one parameter set data point, Senvol predicted that it was likely to be over our target. Marginally over, but over. And again, that takes into the uncertainty. Parameter set B, it's the same situation, but there's more properties taken into account. And again, even though in this case for B prime, Northrop's parameter selection for goal B, there were two empirical data points at that same parameter set. But clearly those were higher in the band of uncertainty or within the range of what you would get over multiple samples tested at that parameter set. In reality, those averages were lower, and that was reflected again when we actually built and tested at that parameter set. So going over kind of like a lot of things that we covered, but just reiterating. So for Senvol ML, even though that the parameters that were selected had no empirical training data, those two parameter sets were able to meet both goals. And that's within, obviously, as Zach mentioned, 220,000 parameter combinations doesn't necessarily sound small, but in the grand scheme of what you actually end up doing in larger, more complex DOEs, this can get larger and larger, and it can only, the results we see here only get exasperated and take more time when you're just trying to go the traditional approach, which Northrop used. And, we were only picking 300 or looking at 300 data points within that 220,000 parameter set. So there's bound to be more iteration, more trial and error, more issues when you're trying to rapidly, find a parameter set that meets the goals of your applications. So in summary, again, Senvol met both goals with each of their parameter sets based on the ML approach, considering the whole design space within each of the parameter set combinations. Whereas Northrop Grumman's approach as an initial approach, right, this was just like the first set of builds, no data. We did not meet the goals. So the likelihood that Northrop would have to go through more iterations to do more DOEs and down select, whereas Senvol ML would already have a good starting point and could really narrow in to validate that parameter set, or maybe optimize it further if you wanted to make a more targeted parameter set to meet certain criteria. And so since then, Northrop Grumman found great value. I mean, obviously, the ML software showed great value in how we can optimize and rapidly develop parameter sets. So we've been assessing ML software for all sorts of additive projects related to both metal and composite materials. With that, I appreciate you guys listening, the work that we did, and we'll open up to any questions.
All right. Thank you very much. We'll now head into the Q&A session. If you do have any questions for our presenter and you haven't done so already, please go ahead and type them into the Q&A space on your WebEx screen now. We do have a couple of questions to get started here. So how many repeats have been used for each parameter?
So this is Zach. Typically, using the machine learning approach, we don't recommend, or the software won't recommend any repeats because it's really just not a very efficient use of resources. In this particular project, there were some repeats because, as Taylor mentioned and I mentioned, we were doing other things in this project, so we needed repeats for other tasks in the project. So it's a little complicated of an answer, but typically, if you were doing parameter optimization or material development, the software is not going to advise on any repeats at all.
All right. Thank you very much, Zach. Okay, let's see our next question here. What type of ML algorithm has been used here? Any result on training and validation of MSE?
In terms of what type of algorithm we use, we consider kind of what happens under the hood to be proprietary. So I unfortunately can't answer that. We can talk about what the software tool does, but kind of not how we get there. And I'm not sure I understand the second part of the question. I'm not sure what the MSE acronym is referring to.
Okay. Yeah, if let's see. If the person who asked the question could send in a clarification quickly, I could follow up on that. Let's see, I have another one here. Let's see, you had mentioned earlier in the presentation that the two machines you were working on had separate serial numbers. Can that make a difference when you're working in a machine learning software? And is that accepted as like same and same?
So it's up to the user to define. The user can define in the machine learning software that those are from different machines, and you can then analyze how much machine to machine and quantify how much machine to machine variability you're seeing. Or if the user wants, they can merge it together and treat it as one data set. But I'm curious to hear Taylor's answer, not on the machine learning side necessarily, but your experience at Northrop with machine to machine and even build to build variation. I'm sure you've experienced a lot of that.
Yeah, I mean it's a very important primary variable. Especially it depends on the company's I guess strategic approach to additive. Some people are outsourcing everything and working directly with suppliers. Some people are insourcing. In the case of insourcing, you know, if you're only planning to use one or two machines for production, I mean, obviously it becomes less of an issue. But even then, build to build does matter. So you use the same machine, but have builds as a variable. Machine to machine, that's a big issue, or I guess challenge in the additive industry, especially when you start talking about different OEMs, machine OEMs, like in the case of a lot of the main processes now, there's just multiple companies out there. But that doesn't necessarily mean you can just take whatever parameter set you've developed from one machine and apply it to the next. There are intricacies within those machines that can lead to different results. And at the end of the day, you want to more sort of target your properties. So I mean, something like an ML approach can probably get you to your goal if you've developed something on one machine at a parameter set, It can use you as a starting point, but help you iterate to develop the same properties in microstructure. Yeah, so I mean, getting to that final state can be tricky without any sort of kind of way to rapidly optimize to that. It's not just a one-to-one, I guess is the quick way and short way to say it.
Okay, thank you very much. Okay, so let's see. Following up on the question earlier, so MSE is mean squared error. So it would be any result on training and validation on the mean squared error.
Yeah,
is that right?
Yeah, so the model, one of the outputs in the software, it'll tell you, like I said, the standard deviation, it'll tell you the root mean squared error, and everything is cross-validating on itself. So when the software gives you a model, it has been cross-validated. And again, I can't go into too much detail, but it's taking some of your data as training data, it's then testing it on a subset of the data that had been withheld. It then does this over and over again many times for different combinations of training and testing data, and then gives you kind of an aggregate model of all of those experiments that have been run in the background.
All right, thanks, Zach. And then I think this is following up on the first question. So I'm also wondering, without any repeats, how is the standard deviation generated for the parameters?
Again, that's getting a little bit too much into what's happening under the hood. All I can tell you is there are certain
Okay.
approaches we take that allow us to calculate uncertainty and standard deviations across the entire parameter space based on the training data.
Gotcha, Zach. Sorry about that. Thank you.
No problem. No problem.
All right. So let's see. I think that's going to wrap up all the questions we have for today. See, I'll wait a second just to see if any more come in. But
Jason, I can maybe add on a comment from a Northrop perspective on like even though the Senvol ML software is using some background calculations and strategies to determine those uncertainties with less replicates. At least right now, there's still no replacement for, at least in the aerospace industry, certain statistical approaches that are needed to get a certain process to a level of maturity that would be accepted by customers. I know that may be different in other industries, and obviously you can get there right away or a lot faster. But there's a lot of work in the industry to figure out how to use machine learning to try and figure out how to more quickly adopt and new materials, new processes, or any process changes. So just figured I'd make that comment.
Yeah, thank you very much for that, Taylor. All right, so that's going to wrap up today's TRX webinar series. I would like to once again thank Zach and Taylor. If you have further questions for either of them, their contact information is here on the screen. And this TRX webinar will be uploaded to the America Makes YouTube channel if anyone wants to follow up, or if you would like to have, send it out to any of your friends. So there will be a post-webinar survey going out to all of those who participated. We do really appreciate the time that you take to provide America Makes feedback so that we can continue to improve and strengthen the additive community. And as a reminder, if you or your organization would be interested in sharing on the TRX webinar series platform, you can find the link on our website at americamakes.us, or you can fill out the form that follows the presentation today. Or you can reach out to myself, jason.thomas@ncdmm.org. Thanks, everyone, and have a great day.
Thank you, everyone. Thanks, Jason. Thanks, Taylor.
Thank you.